Hi class, welcome to our first lectures on chapter 5 for quantum mechanics. Our main reference is Introduction to Quantum Mechanics by David J. Griffiths, and as I've always told you, I recommend this book and get a copy of this book, and you can buy this online. Chapter 5 is about identical particles, but to start with that discussion, let's start with two-particle system. So for a single particle, the wave function was very simple. The wave function was just this one, as we discussed in chapter 1, and it's always a function of space and time. So we don't include the spin yet, the wave function for spin. Now for two particle system, the wave function will now look like this. It's now a function of the location of the first particle and the location of the second particle and time. And of course, again, the time evolution or this wave function still follows or has still to be satisfy the Schrödinger equation, which is this one. The Hamiltonian will now be an extended one. So for only one particle, the Hamiltonian would just be two terms. The h bar over 2m del square of something plus the potential. Now that you have two particles, you must have the kinetic energy or the associated kinetic term of the Hamiltonian for particle 1 and for particle 2. So your Hamiltonian will now look like this. There are three terms, and of course the third term will now have a potential that's dependent on the locations of the two particles. And of course in general it should be dependent on time, but there will be a special case that the potential is independent of time. So the statistical interpretation, which was done in a single particle system, now becomes psi square that should be integrated both on the two particles. So you have psi r1 r2 t square, now to be integrated with the position r1 and position r2. So here again, the psi must be normalized in such a way that the integral is always equal to 1 from, this is all space. So we can separate the variables, the space and the time. So your first part of the wave function would just be a function of space, and then of course we have this as a function of time, the exponential, the solution to the differential equation that's only dependent on time. So now you have a time independent Schrodinger equation, which is this one, for two particles, for two particle system. Now you may ask the question, what about identical particles? And how about if they're bosons or fermions? Bosons are particles that can occupy a single space, where all bosons can occupy there. How about, but there are also identical particles we call fermions, in which only one particle in the space could occupy, and only that one, or maybe two with an opposite spin. But suppose particle 1 is in the phi A state, and particle 2 is in the phi B state. So in this case, your psi or phi R1 R2 would be this one here. You can separate the two particles, so you can have the wave function of the particle A and wave function of particle in particle 2, which is phi B, for particle 1, which is phi A. So in this case, you are assuming that the particles are distinguishable, meaning you can determine them. But how about when they are not distinguishable, or they're identical? In classical mechanics, all particles that we study are determinable, or distinguishable, such that we won't overlap with the other particle. Then we would just be able to make superposition of the results of these particles, so that we arrive in a classical result. For quantum mechanics, since we're dealing with very minute particles such as electrons or protons, there's only one electron. An electron is an electron, or you cannot tell an electron from one point and an electron in another point. They're all identical. Even the protons are all identical. And you won't even know that they have changed places, because all of them are identical particles. So, to accommodate this in quantum mechanics, since in classical mechanics we know the particles exist and they are distinguishable, but in quantum mechanics, particles can be identical, and of course in quantum mechanics we're dealing with very small particles, which is very impossible for us to paint colors on the particles or label the particles, because they're absolutely identical. So in order to accommodate the particles to be identical, or indistinguishable particles, we construct a wave function that is non-committal. Non-committal. So there are two ways to do it. This one here. So we set phi plus to be the non-committal wave function for bosons, and phi minus for fermions. So you just take note of the sign for plus for bosons and plus for minus for fermions, and you can see here that you can see from here that your phi AR1 becomes, in the second term, you're accommodating your particle 2 on phi A, and on the first term you have phi B R2, which is for particle 2, but now on the second term you're accommodating particle 1 on phi B. So again, plus is for bosons and minus is for fermions. So examples of bosons are photons and mesons. So in fact, you can put a lot of photons in a single place. And for fermions, you have protons and electrons, because these are half odd integer particles. By the way, bosons are particles which have integer spins, while protons and electrons are half odd integer spin particles. So that's also one way of identifying bosons and fermions. So in this case, you can see that it follows, the non-committal wave function follows that there is only one particle that can occupy one place. So identical fermions cannot occupy the same state at the same time. Two could only be one. So the wave function there would be 0 for fermion if you put two particles in one place. Two fermions in one place. So by the way, we have here the exchange operator we call P, which interchanges the two particles. So for example, if you have a function which is a function of R1 and R2, and then if you apply P, the two particles will exchange places. So if you apply P twice, then the particles will just go back to their places. Hence you have the eigenvalues of P to be just positive or negative 1. If two particles are identical, the Hamiltonian must treat them the same. So you have your mass equal to m, for example, for all particles that are identical, and then your potential should be also symmetric here. So in this case, it follows that P and H are compatible observables, meaning that if you do this, P on the Hamiltonian would just be equal to Hamiltonian times P. This means that they commute. So again, you have the wave functions. If the two particles exchange, when it is positive, that would be bosons. But if the particles, if they exchange, the wave function becomes negative, that would be fermions. So you have to note this also, that if a system starts out in such a state, it will remain in such a state. So this is very important here. This one is very important. So, for example, suppose we have two non-interacting particles, both of mass m, in the infinite square well. The one particle states are this one. We have solved this in chapter 2. Now, if there are two particles and the particles are distinguishable, the composite wave functions are simple products. So you have here phi or psi n1 n2 x1 x2, then you will have this one, just the product of the two particles. And of course the energy would just be the sum of the energies of each particle. That's for distinguishable particles. For example, the ground state is you have 2 over a sine pi x1 over a and sine pi x2 over a. And of course here your n is equal to 1, and also n is equal to 1 here, so that your energy would just be 1 plus 1 square plus 1 square times the times the energy K. So for the first excited state, so the one particle would be excited, so the n there would be 2, say for x2, and for x1 or the particle 1, it remains the same, n equals 1. So for the other excited state would be for the first particle x1, n equals 2, and the second particle x2, n equals 1. the energy for both of these would be 5k, because that's 1 square plus 2 square equals 5 square. It's equal to 5, not 5 square. So if you want to go to the second excited state, what would be the second excited state? The second excited state would be when both particles are in the first excited state. So that's n equals to 2. So you will have 2 square plus 2 square would be 8k for the energy, 8k. Now, if the two particles are identical particles, the ground state is unchanged, but the first excited state is non-degenerate. By the way, if you say degenerate, that means they have the same energy. In this case, for distinguishable particles, the first excited state is degenerate. This means that they have energy that are equal. So this one has an energy equal to 5k, and this one also has an energy 5k. But for indistinguishable particles, say for example identical bosons, the ground state is unchanged. So you will have the ground state to be having an energy of 2k, but the first excited state will have 5k, but there's only one state for that 5k. And for the identical fermions, there's no energy state with 2k, but the ground state is 5k. Why is that? Because you cannot put two particles on the same state. So if for bosons you can have two bosons in the first or in the ground state, but for two fermions, one should be in the ground state and the other one should be in the excited state, the first excited state or the other excited states. So this means that your ground state energy for fermions is 5k. Now, suppose one particle is in phi ax and the other particle is in phi bx, and the two states are orthogonal and normalized. So if the two particles are distinguishable, the number 1 is in the state 1, and your combined wave function would be this one. Will be this one. But if they are bosons, your composite wave function would be here. The 1 over square root of 2 is necessary because they are normalized functions. So you have to divide by the magnitude of the coefficient of the two functions. So here, and then for the identical fermions, you have this one. The only difference between equation 5.16 and 5.17 is that you're using minus instead of a plus. So we will now calculate the expectation value of the square of the separation distance between the two particles. So of course the expectation value for the square of the difference of the distance between the two particles would be just this one, and this just being squared, no, you have x1 squared plus x2 squared minus of the expectation value of the product of x1 and x2. Now we will calculate first for distinguishable particles. So this is for x1 square. This is of course the equivalent integral of this is just x1 square times the wave function of the first particle dx times the wave function of the second particle square integrated with respect to x2, and then you will have this this one would just be equal to 1, and so you have this is just x square, the expectation value of x square of A. So it's only this integral that determines the result. And of course for x2 in the same manner you will have this result. And of course for x1 times x2 you will have this one. Now we'll go to identical particles. So we can combine the computation. We just take note of the signs here, plus for bosons and negative for fermions. So here we have this result. For x1 we have this. We have this one. If you try to look at this, you have 1/2. This is 1/2 because that is square root of 2 square, and then you have x1 square. This one will determine this term, and of course this is equal to 1. This one will also determine this term, and this one will just be equal to 1. But this one here you have both are 0. Because the two wave functions are orthonormal. So the integral here is equal to 0, and the integral also here is equal to 0. So that's why you have That's why you have two zeros here. So for identical particles, you will have 1/2 x square a plus 1/2 x plus 1/2 x square of b. So similarly, if you calculate for the expectation value of x2, you will also get this. But now, how about for the product? So here you have x1 and x2 would be on this side. So you have x1 here also and x2 for this one. But this time, this one here is not anymore zero. Not anymore zero because they are there's already a term here in front. So that will give you the answer of this one. This one plus some expectation value which is equal to this, of course the 1/2 there will cancel. They will just be the same. So your expectation value of x AB would just be the integral of x psi A of x, that's the complex conjugate, times the psi B of x integrated with respect to x. So what is the implication of this? Evidently, you will have this one. If you compare this equation with 5.19, there's an extra term in 5.21. And look, this is the extra term. So what does it mean? By the way, the negative here is for the boson. Yeah, because you have it's supposed to be minus, because that's square. This is supposed to be minus for minus, but you have to multiply another minus so that you will have negative for boson and positive for fermions. And so for identical bosons, the upper sign, which is negative, tend to be closer together. So if you have two bosons near each other, they tend to be closer to each other, like they're sort of attracting each other. While for identical fermions, the particles are set apart. So that is also very that's also an expected result, because like in a state you can put many bosons, and if you put many bosons, of course they would like to lump with each other. And then of course, for fermions, because only one particle can stay, or can be accommodated in one state, so the other particle should be in another state, and so they tend to be really far apart. Note that the expectation value of xab vanishes unless the two wave functions actually overlap. If psi ax is 0 whenever psi bx is non-zero, then 5.20 would be 0. So if you, as I've told you, that there is some sort of force of attraction between identical bosons. They're pulling themselves closer together, while for identical fermions, they're repelling each other. And this phenomenon is called exchange force. Although it is not really a force at all, no physical agency is pushing on the particles. It is purely geometrical consequence of the symmetrization requirement. Which is a quantum mechanical phenomenon. Now consider a hydrogen molecule H2. What is a hydrogen? You have a proton, and revolving around that proton is an electron. And also, that's for hydrogen. And for the hydrogen molecule, you have two electron proton system. So the ground state consists of one electron in an atomic ground state centered on one nucleus, and one electron in the atomic ground state centered at nucleus 2. So if electrons were bosons, the symmetrization requirement would tend to concentrate the electrons towards the middle, here. But the electrons are fermions, so they have to be here. So here, like, if your electrons are bosons, you would form covalent bond of the two molecules. But the electrons are not bosons. So that your electrons would tend to be farther away from each other. So you have here electrons. They don't stay close. So you have your electrons are shifted to the wings and tearing the molecule apart here. Now, if we include spin, the wave function would now be looking like this. It's a product of wave functions of space, and of course the wave function of the spin. So in the absence of the coupling between spin and position, it is assumed that the state is separable in its spin and spatial coordinates. Or the spin is independent of the location of the particle. Now, in the presence of coupling between the location of the location of the particle and the spin, the general state would take the form of the linear combination of this is for spin up and this is for spin down. You can see the minus sign. The positive sign is for spin up, and the negative sign would be for spin down. But you have here a minus because, why is that? Because they are fermions. So when the two electron states are put together, not just the spatial part that has to be antisymmetric with respect to exchange, also the spin. For two particle system, for two electrons, for a singlet combination, the singlet combination has total spin of 0, while the triplet combination would have equal to 1, so that would be 1, 0, and -1. So the triplet states are all symmetric and would require an antisymmetric spatial function, while the singlet combination would have to be joined with a symmetric spatial function. If you look back in the lecture of chapter 4, evidently the singlet state would lead to bonding, and the triplet would lead to anti-bonding. Here's an important note here. Chemistry says that covalent bonding requires the two electrons to occupy the singlet state with total spin of 0. Now we'll go to atoms, and the first atom that we will discuss would be that of helium. But before that, let's look at the atom. A neutral atom of atomic number Z consists of a heavy nucleus with Z protons with total charge of Z times E, and they are surrounded by Z electrons with mass M and charge -E. So in general, the Hamiltonian for the system would be this one. So if you look at closely, you have the first is the kinetic energy of the electron, and then you have the interaction of the electron on the nucleus, and then you have the interactions of the electrons with the other electrons. So you have Rj and Rk here. They should not be equal. So I'll just read the caption there. The term in the curly brackets represents the kinetic plus potential energy of the jth electron in the electric field of the nucleus.